Hi, this is Enrico Reggiani from Barcelona Supercomputing Center, and in this video I will present our ASPLOS'22 paper called BiSone-e, a lightweight and high-performance accelerator for narrow integer linear algebra computing on the edge. I will start with some context definition that will explain the rationale behind our work, and then I will talk about binary segmentation, which is the mathematical technique that we are using in order to reduce the arithmetic complexity of narrow precision blast computations. Then I will present BiSone-e, the proposed architecture, and then I will show you the experimental result and the conclusions. Let's start with some context definition. So modern head processors require high performance and also have to respect tight constraints in terms of power and area. As many applications like deep learning, instant matching, the target edge computing devices rely on blast computation based on narrow integer, it's increasingly important to accelerate this type of application by keeping area and power footprints as low as possible. However, current hardware architecture are currently either over-provisioned or under-provisioned for this type of tasks. On the one hand, general-purpose processors are not optimized for narrow precision computation. It is worth noticing that the typical minimum bit width supported by a processor is 8-bit, and on the other hand, application-specific accelerators, while featuring high performance, are tied to a specific set of application class and a typically area-hungry device. And for this reason, we propose BiSone-e, which is a microarchitecture that aims to fill the gap between these approaches. On the one hand, BiSone-e shows comparable or more performance than a high-performance vector processing unit for narrow integer computation, while featuring 600 less area. And on the other hand, BiSone-e shows more flexibility than an application-specific accelerator. Let's talk now about binary segmentation. Binary segmentation is a mathematical technique that allows to decrease the storage space and the arithmetic complexity of matrix and vector computation based on narrow integers. Starting from very simple operations like the addition, the subtraction, or the reduction between the vectors, and arriving to more complex computations like the inner product and the linear convolution, which are the kernel that we will consider in this work. Let's consider a vector V containing n element of maximum bit width p. With binary segmentation, it is possible to express this vector as a single integer, which every slice of the integer is composed by a specific element of the vector. The bit width of each slice of the integer element, composed by binary segmentation, has a bit width called clustering bit. If the clustering bit is equal to the actual maximum bit width of the vector, binary segmentation allows data compression in memory. For example, we can think that if the clustering bit is equal to b, which is equal to 4, we can compress up to 16 elements in a 64-bit variable. On the other hand, if the clustering bit is greater than the actual maximum bit width of the vector, binary segmentation enables to perform single instruction multiple data computations. Let's see an example. Imagine you want to compute the inner product between these two vectors containing 2 elements and a maximum bit width of 3. In order to do that with a standard algorithm, you would require 2 multiplication and 1 additions. However, with binary segmentation, you can compute the same computation with just a single multiplication by following 3 basic steps. The first step requires to cluster all the elements of the vector in a single variables. You can see this variable depicted in V in green here and called U and V by following a clustering width which is specified by this formula. Then you have to multiply these 2 variables, and as a third step, you have to extract a specific slice of the result of the multiplication to obtain the final inner product. And as you can see in this example, we just used a single multiplication in order to compute the inner product between these 2 vectors, thus saving 3x the arithmetic complexity with respect to the standard method. Similarly, if you want to compute the linear convolution between these 2 vectors via the standard method, you would require 8 arithmetic operations between multiplication and additions, while with binary segmentation, it is possible to perform the same computation with just a single multiplication. Similarly to the case of the inner product, it is necessary to express the input element as single variable, each variable having a specific clustering width specified here. You have to multiply the two variables, and then for each slice of the multiplication output, you obtain one output element of the linear convolution, where each element still has the clustering width as a bit. And as you can see, we obtain the same result as computing the linear convolution in the naive way, while saving 8x the number of arithmetic operations. So as a first contribution of the paper, we performed a design space exploration of binary segmentation to quantify the benefit of implementing binary segmentation-based computation on current scalar pipeline of general purpose processors. And as a first step of the design space exploration, we quantify the number of elements that can be clustered together with binary segmentation in order to compute either the inner product or the linear convolution. We call this set of elements as input cluster. And as you can see from the image, for a 32-bit architecture, it is possible to cluster from 2 7-bit elements up to 6 1-bit elements. While for a 64-bit architecture, it is possible to cluster from 2 15-bit elements up to 10 1-bit elements. And for the inner product example, that means that we can save in a 64-bit architecture from a 3x the arithmetic complexity for a 15-bit base computation up to 19x the arithmetic complexity for 1-bit computations. And similarly, for the linear convolution, it means that we can save from 2.5x up to 19.5 x the number of arithmetic operations, so the number of multiplication and addition required to perform the upper multiplication. However, our design space exploration shows that binary segmentation introduces overhead in the overall computations. And these overhead are mostly due to creating the input clusters or extracting the output elements from the multiplication results. For example, in the inner product, we found that the pack phase, so the phase in order to create the input clusters, amount from the 50% to the 85% of the total computation time. While for the linear convolution, the extract phase amount from the 50% to the 55% of the overall execution time. And it is the dominant part of the computation at the end. And this is because for linear convolution, binary segmentation is producing multiple elements per cycle, and so it is more difficult to extract every element than in the inner product example. And for this reason, we propose the BiSone architecture, because although our design space exploration shows that binary segmentation offers a substantial improvement for narrow precision plus computations, these improvements are alleviated by the lack of ISA support and by the lack of functional Unix extension present in the current general purpose processors. And this is because general purpose processors doesn't include operation or specific functional unit to create the input cluster needed by the binary segmentation or to extract a specific output from the multiplication output. For the reason we proposed BiSone-e. BiSone-e is an hardware architecture that offers hardware and ISA support to enable binary segmentation-based computation at the edge. And it offers a minimal ISA extension to compute the inner product and the linear kernel on scalar processors, and hardware unit that efficiently perform the pack and the strat vector operation. So the operation required to create the input cluster and the one required to extract a specific slice of the output from the multiplication results. We also want to highlight that BiSone-e is not an accelerator, but is an architecture, a microarchitecture that is integrated in the main processor pipeline. This slide shows the microarchitecture of BiSone-e. BiSone-e is composed by two main processing stages, the pre-processing stage and the post-processing stage. The pre-processing stage is composed by two functional units. The pack unit is used to keep data compressed in memory, and so use binary segmentation to compress data, while the extend unit is used to create the input clusters. The input cluster created by the extend unit are then forwarded to the actual 64-bit integer multiplier of the processors, and the result of the multiplication is processed by the mask unit. Depending on the instruction that is being decoded, the mask unit acts in different way, meaning that it masks different region of the multiplication output depending on the instruction decoded. The output of the first unit is then sent back to the register file. As you can see, a control unit is used to orchestrate all the data movement of the pre-processing and the post-processing stage. In terms of instruction, we can see that we added 5 different custom instructions to the RISC-V ISA. The BS set instruction configures the control register with one of the possible configuration of the control parameter list. The control parameter list contains all the information required to correctly perform binary segmentation, like the input data bit width, the number of elements contained in the input data, the dimension and the bit width of the input cluster, and the number of iterations required to process a complete 64-bit register. The BS pack is used to pack data and to keep data compressed in memory, while the BS-EP is used to compute the inner product, and the BS-LCL and the BS-LCH instruction are used to compute and return the lower slice and the higher slice on the linear convolution. Because remember that the output of the linear convolution is a 128-bit result. And so the output that had to be written back in the register file has to be partitioned into different instructions. Let's now talk about experimental evaluation of BiSone. As for the experimental evaluation, we implemented all the microarchitecture of BiSone and the ISA extension using the Gen 5 simulator, targeting an in-order scalar processors, and we consider 2 different case studies. For the inner product, we consider the quantized neural network workload, while for the linear convolution, we consider approximate stream matching algorithm composed by 1-bit linear convolutions. We compare the performance of BiSone with a Gen 5 based RISC-V BPU, and we estimate the power consumption using the MacPath simulator. Finally, we integrate BiSone on an in-house scalar in-order processor up to place and route phase in both 65 nanometer and 22 nanometer in order to estimate timing and area consumption. We started our experimental evaluation via micro-benchmarking. In particular, we computed both the inner product and the linear convolution kernels with BiSone, and we compared the obtained result with the same algorithm computed by the naive implementation or by exploiting binary segmentation using the standard RISC-V ISA or the RISC-V ISA extended with bit manipulation instructions, like the pack and the extract instruction. As you can see from the images, for both kernels, BiSone outperforms all the other implementations. For the inner product, by a factor that ranges from 4.4x up to 22.6x, while for the linear convolution, by a factor that ranges from 3.5x for 8-bit based computation up to 61x for computation based on 1 bit. It is also necessary to note that with BiSone, the speed up obtained scales with the input data bit width, while for the other implementation, like the using binary segmentation, this doesn't happen. And this is because the pack and the extract phase had overread in the computation. And so, although we have a speed up with respect to native implementation, we doesn't see a scaling in the performance. Then we computed 2 convolutional neural networks named AlexNet and VGG, and we compare the results of BiSone with 8-bit, 2-bit, and 4-bit with respect to 2-lanes VPU based on RISC-V. As you can see from the images, from a performance standpoint, BiSone shows comparable result with respect to the VPU with a 4-bit implementation and outperforms by a factor of roughly 2x the VPU for 2-bit implementations. While in terms of energy efficiency, BiSone is always better than the VPU. From a factor that ranges from 1.5x for 4-bit based computation, up to 3x for 2-bit based computation. And we see similar result for the VGG16 neural networks. The 4-bit based BiSone implementation shows comparable results with respect to the vector processing unit, but at 2-bit, BiSone outperformed the vector processing unit by a factor of 2x. And from the energy efficiency metric, BiSone at 4-bit outperforms the VPU by a factor of 1.8x, and at 2-bit by a factor of 3.6x. Regarding the approximation matching benchmark, we used an algorithm that requires to compute 1-bit Boolean linear convolution, and we consider a dataset composed by 4-letter alphabet and another dataset composed by 256-letter alphabet. As you can see from the images, BiSone outperforms from 22x to 61x faster compared to this current implementation, and 1.3 to 3.2 faster with respect to the VPU. In terms of energy efficiency, for both the datasets, BiSone show better efficiency compared to the scalar core and the VPU by a factor that ranges from 40x to 5x. Finally, concerning the area and power analysis, we integrated BiSone in an in-house SoC running synthesis place and route in both 65 nanometers and 22 nanometers. And in both technology, BiSone doesn't introduce critical path in the design. And the area overhead of BiSone in the whole layout is below 0.07%. That means it is more or less 600 less area consuming than the VPU. You can see in the right the area that consumed BiSone in green and circled in black. Finally, the final contribution to the total power consumption in both technology is lower than 0.04%. To conclude, we can say that BiSone, together with binary segmentation, allows to optimize narrow precision plus computation on modern edge devices. Indeed, BiSone achieve high performance and allow to save memory space. With binary segmentation, that allows to reduce the arithmetic complexity of kernels like the linear product and the linear convolution by factor that ranges from 2.5 to 90.5x, BiSone is capable to reach the same performance of an high-performance vector processing unit. Moreover, in terms of area and power, it shows roughly 600 less area compared to the VPU and accounts for the 0.04% of the total processor power dissipation. And finally, the same methodology used in BiSone can be extended to other general-purpose architecture, like VPU, GPU, and FPGAs, enabling for that architecture the same benefit that we studied in this work. Thank you for your attention. Feel free to contact me to my institutional email if you are interested to know more about BiSone.